Okay, this is the video for 16.3, which is for Calc 3, which is line integrals computed using the fundamental theorem of line integrals. So this is actually a technique which will allow us to compute certain line integrals for vector functions as the integrand when the field is special, something called a conservative vector field. And in that case, we'll be able to find something called the potential function and then use this thing called the fundamental theorem of line integrals to compute more easily than we would otherwise. All right, so we're going to take a look here. 16.3. Make sure I'm presenting. Yep, okay. All right. So first of all, we need to recognize that some fields are special. Okay, let's take a look at a first example of a field that isn't special in this way. Let's say that we have a field f, which is defined with x component y squared, a y component is x, which can be written as a PQ, right? So I don't know that I made a big enough deal about this in the last video, but this P and Q is just the x and y components of the vector field, all right? And so sometimes it's written this way, where the x component is multiplied by the little change in the x direction and the y by the y, because if you have a small change in x, then this sort of represents how much the field is changing just per changes in that direction, and this adds on the amount that's changing in the y direction. Okay, so typically it would be written something like this, but what that's telling me is that the field that we're integrating is y squared for its x component and x for its y component. Okay, but we're going to evaluate it between two endpoints, between the point -5, -3, and 0, 2, but we're going to do that along two different paths. Okay, so one path will be a line segment that goes from right directly between 2 points, and another one is we're going to involve a parabolic curve. X equals 4 minus y squared will go through those 2 points. So we will we'll follow that curve as well. So these two paths would have different parameterizations. For the line segment, we would use the standard line segment path, which is 1 minus t times the initial position vector plus t times the final position vector, right? And so here's the initial position vector to the starting point. Here's the final position vector to the ending point. And then 1 minus t times that. If you multiply it out and get all the x and y components together here, right, you end up with 5t minus 5 for x and 5t minus 3 for y, which means the parameterization is x is 5t minus y and y, or sorry, 5t minus 5, and y is 5t minus 3. And for the standard parameterization, the parameter t goes between 0 and 1 for line segment. Okay, so we have a parameterization, and that means we have a position vector over here, which is it's going to be 5t minus 5 for x, and it's going to be 5t minus 3 for y. So the result of the parameterization is a position vector. Okay, over here with the curve, there's different ways we could parameterize, but since this x is solved already in terms of y, why don't we just make y the parameter? We'll just relabel it t and then rewrite x in terms of that. So that means that the position vector is 4 minus t squared, because it's 4 minus y squared, and we're allowing y to just be t. And so then that means that we have to have t go from the y value -3 to the y value 2. So t is going to go from -3 to 2, and this is the position vector. All right. So now we have two different parameterizations. And then what we'll do here on this screen is we'll do the line integral. So to do the line integral for a vector, we have to evaluate f evaluated at r and dot product with the derivative, right, over the parameter region, right? So we'll go through that process. First, we have our r. Then we would use that to take the derivative. Work with the line segment one here first. So the derivative of the x would be 5. The derivative of the y would be 5. And then because I have my function f is y squared x, then I'm going to use these. This is going to be x and this is going to be y. So I'm going to replace in the field equations here, I'm going to replace all x's with 5t minus 5 and all y's with 5t minus 3. So this becomes 5t minus 3 squared, and then this one becomes 5t minus 5. Right, so that's the function evaluated with r, in other words, just substituted it with the parameters. And so we now need to take the dot product of this derivative vector and that. So we take the dot product, and when you multiply the x and y components together and then add, you end up with this. And now we have to do the line integral. So we're doing the integral of that with the parameter going from 0 to 1. And you do the normal fundamental theorem stuff, and you get negative 5 6. Okay. All right, so that's the sum of all of the effects of this field as we move along this path. It sums in some way up to negative 5 6. Okay, if we do the same thing over here for this path, we have different parameterization. F is still the same, but what happens is when we parameterize it by plugging in what x and y are, we have different expressions for x and y. So that means that this y gets replaced with t, so t squared, and this x becomes 4 minus t squared. And then when we take the position vector and we take the derivative, we get a different derivative vector, a different tangent vector here, negative 2t1. We take the dot product, we get a different dot product. And therefore, when we integrate that from the parameter limits, which are now negative 3 to 2, we end up getting a different value, right? This was positive 254 over 6. So what that means is this field is constructed in a way that if you move along this path, the summation of the field's effects add up to negative 5 6. But if you move along this path, the summation of the field's effects add up to 245 over 6. And that's generally true for fields, that they're not path independent. In other words, it depends which path you take, even if you're going between the same endpoints. Okay, but not all fields are like that. Some fields are special. So here's a different field, seemingly more complicated, where the x component of this field is 3 plus 2xy, and the y component is x squared minus 3y squared. Let's take those same two paths so I don't have to go through the reparameterization. I have the same position vectors, but let's compute the line integrals along those two different paths for this integral, or yeah, this field, okay? So if you go through the process, take the derivative, you plug this into the field equations, right? Substituting x and y in here, right? And then carefully integrating over the parameter from 0 to 1, you get 55. So that means as we go through this field along this path, the sum of the effects of the field add up to 55, okay? And then if you go along this path, and you carefully go through all the steps here, you can follow it along in positivity if you want, you end up getting 55 again, right? So when we went along this path, we also got 55. So the sum of the field's effects ended up the same, right? And in fact, in this kind of a field, we could have gone along any path as long as we started at this point and ended at this point. The sum of the vector field's effects would end up being 55. And if that's true, then the vector field is special, and we call this vector field a conservative vector field. Okay, so conservative vector fields have the property that the value that you get in a line integral depends only on the endpoints that you decide to start and end on, but not on the path that you take. Now, if I'd have picked a different endpoint, if I wanted to go from here to here, right, using some path, I may have gotten a different number, 31, let's say, right? But it would be the same, just it only depends on which particular endpoints you use. Okay, so that's called a conservative vector field. It'd be nice if there was a test for us to recognize when we do have a conservative vector field, and it turns out that there is, right? This vector field here that we did in the second example was conservative, but this one in the first example was not. How can we tell? Well, it turns out that if you define the x component, so for a vector field with 2 dimensions, if you define the x component as p and the y component as q, if you take the derivative of the x component with respect to the y variable, partial derivative, and you take the partial derivative of the y component of the field with respect to x, if those two things are equal, then the vector field is conservative, okay? And there are ways to tell whether vector fields for 3-dimensional domain are conservative. We're going to have to wait till something we cover in a later section before we can do that. There's an equivalent to this later. But for right now, we're going to stick with just 2-dimensional domains, x and y only. And this is the way we test. If those partial derivatives are equal, then that means that the field is a conservative field. So, for example, the one we did in the first example, that's this one over here. If we were to check that, right, this is the p, this is the q. And so what is partial derivative p with respect to y? So if you take y squared and take the derivative with respect to y, you get 2y. But if you take the partial derivative of the y component with respect to x, you get 1. And since those things are not equal, this field was not conservative. And that means when we do the line integral, it very much depends upon which path we go along, right? But in the second example, we have this one, right? And if we define this as p and this is q, then the partial derivative of the x component of the field with respect to y, right, would turn out to be, this is the only variable here, so this is a constant, so it's 0, so the derivative is 2x. And then over here, if you take the partial derivative of the y component with respect to x, you get 2x, and this whole thing's a constant. And since those are equal, that's how we can detect that this is a conservative vector field. All right. Okay, so now that we know how we can identify a conservative vector field, how does that help us? Well, it turns out that if a vector field is conservative, not only will you get the same vector line integral regardless of the path that you take, but there's this alternate way to compute the line integral, which is sometimes easier. Remember the fundamental theorem of calculus, technically part 2, the one we use all the time, where if you have a function and you're taking an antiderivative, a definite integral from a to b, you just need to evaluate the antiderivative of the integrand and then plug in the endpoints, end minus start, right? Rather than resorting to things like Riemann sums or something like that. This states that the sum of the effects of this function over the entire integral are determined only by the endpoints, but it's the value of the antiderivative at the endpoints, okay? Well, there's something similar for conservative vector fields for vector line integrals. And that is that if you have a line integral for a vector field, and it happens to be conservative, there is a function that you can find where you can plug in the endpoint of the function and the start point of the function and subtract the two, and you'll get the same value as if you integrated carefully along the path, along any path, right? Now, this particular function here is called a potential function. It's a potential function of the field, and it's conceptually similar to the antiderivative of the field, okay? So we're going to learn next how to find this potential function once we've determined that we have a conservative vector field. So there's a theorem that states that if a field is conservative, there exists a potential function f of xy. And what makes it a potential function is that if you were to take the derivative of the potential, you would get the original field. So the way, since we have multiple, we have an x and a y component, the derivative of the potential function is the gradient. So if we take the gradient of f, which is partial derivative in the x direction for its x component, partial derivative of the potential function in the y direction for its y component, then that would be set equal to the vector function. So if we can find such a function where the derivative of the functions x and y, the partial derivatives for x and partial derivative of y match the x and y components of the field, then we can use this potential function just to plug in start and endpoints to evaluate. Okay, so let me show you an example of how we compute this potential function. Okay, it's kind of a neat little process. So for our conservative vector function, which was this, we had f was defined by a p and a q here, right? And we know that there is some function, because this is a conservative field, we've checked it, such that the derivative, the gradient of that function, so partial derivative f, partial derivative y, will be able to be equal to these two things here. So starting with this definition, we know that the partial derivative of this potential field with respect to x must be equal to 3 plus 2xy, and the partial derivative of this potential field with respect to y has to be equal to x squared minus 3y squared. So the way we compute this is we start with the f1, or the x1, and we say, all right, if this is true, then let's just take the antiderivative of both sides of this. Okay, so if we take the antiderivative of f of x, we're going to get the antiderivative of 3 plus 2xy with respect to x, treating x as the variable. And we can compute this antiderivative. So this would be 3x plus x squared y plus some constant. Okay, now that constant has to be a constant with respect to x. But it actually could be a function of y. Like if this was, say, y squared, when we took the derivative of this, we would get 0. Same as if this was just the constant 3. So for the integration constant, instead of just reporting that as a c, we're going to say that that integration constant could be any function of y, including just a c. So we'll call that function g of y. Okay, now to establish what g is, what we're going to do is say, all right, let's take, so the left-hand side is the antiderivative of the derivative of the function. So that's a representation of the function we're after, the potential function, right? So the potential function xy is going to be whatever we got, 3x plus x squared y plus this gy. If we now take the derivative, partial derivative of both sides of this with respect to the other variable y, then this side would become fy. And we can compute this. This would be the partial derivative with respect to y of 3x is 0. The partial derivative here, this is the variable now because we're dealing with y, would just be the constant x squared. And then the partial derivative of this unknown function g is g prime of y. Okay, in other words, prime being with respect to y. Okay, and so that has to equal, that is equal to the partial derivative with respect to y. But we know that for this potential function, that fy must equal the y component of the field. So we just force it to be equal to that. And then that means that we can solve for whatever the g prime of y is. So because these x squareds are on both sides, it means the g prime of y has to be negative 3y squared. And once we have that, then we can just take the antiderivative of both sides of that to get what the g function is. So the antiderivative of the derivative of g is just g of y, and the antiderivative of negative 3y cubed is negative y cubed plus some final integration constant. Okay, and that one will be an actual constant. Okay, so then we just substitute this expression back into here because that was, at that point, the potential function. So now our final potential function, f as a function of x and y, is the 3x plus x squared y, and then plus the g of y, which was negative y cubed plus a k. This is the potential function. It's sort of conceptually the antiderivative of the vector field. All right. And the reason why that's nice is now that I have that, I can use the fundamental theorem of line integrals to evaluate by just plugging the endpoint points into this function. So the way we would go about evaluating this is first we would check to see if the function is conservative, which we would show that, yep, these are equal. Then we would go through the steps we just went through to figure out what the potential function is. And then we would use the fundamental theorem of line integrals to evaluate, because this is equal to this potential function with the endpoint plugged in minus the potential function with the start point plugged in. So we just take two copies of this function, we ignore the integration constant, we take those two, and we plug in the points. But in this case, we're plugging in the x and y values. So we would plug in the endpoints, which are 0, 2, into the first copy, and then we would plug in the start into this copy over here. Okay, and then you evaluate, and lo and behold, we get that same 55 that we got when we went to the trouble of doing the actual integration along the path. So that's the main idea here in 16.3, is that we have this additional way to evaluate a line integral in the event that we detect we have a conservative field. We can find this potential function and then use this fundamental theorem. All right, so let's take some examples and we'll look at these. Oh, one more thing. If you have a conservative vector field and you start and end at the same point, then that is referred to as a closed path. Okay, and for a closed path, if you happen to have a conservative vector field, that means that you're going to be plugging the same point in for start and end, so that will always be 0. So the result of a conservative, of a closed path conservative line integral through a conservative vector field has to always be 0. In other words, the sum of the effect of this field, whatever happens along the way, has to be completely undone by the time we get back to the start. Right? Now that won't be true for non-conservative vector fields, but for conservative vector fields, this sums to 0. That result has some applications in physics. Okay. All right. Let's go ahead and do some examples. Before we do that, though, we're going to eventually we're going to add on to this. This is the first time we've shown this, but we're going to be able to build a tree of different ways that you can find integrals for vector calculus. And we're starting with line integrals here. So the first question we might ask ourselves if we're presented with a problem is the integrand a scalar or a vector function? Right? If it's a scalar function, then we have to use the scalar version of a line integral, right? Which has us finding the derivative and the magnitude of the derivative, and then evaluating the scalar function over that parameterization of the curve. If we have a vector function, then the next thing we should do is ask ourselves, is the vector field conservative? So if we write the field as PQ, right, are the two partial derivatives equal? If they are, then we're going to use our new ability to find a potential function, and then we will use the fundamental theorem here with the endpoints to find the line integral value, right? But if it's not conservative, then we're going to have to do the more general f dot d. I don't know, these arrows got moved around somehow. Yeah. So we would have to use a more general approach in that case. All right. All right, so we're focusing right now mainly on this case here for today's homework because we're going to deal mostly with conservative vector fields, but this is just one in a series of the different techniques we're building for finding integrals for vectors. All right, so the first question here, similar to homework, would be determine whether or not this function is conservative. If it is, find a potential function. So let's work this together. You can pause the video and try it. First thing we would do is declare that p and this q, and we would check to see whether the partial derivative of p with respect to let's see, that's the x, so with respect to y is equal to the partial of q with respect to x. So the partial derivative of p with respect to y is, this is a constant, so it's 0, right? And so it would just be the derivative of this term is 1 times -3, okay? And over here, the derivative of this with respect to x is -3, but 0 and 0, so sure enough, this is conservative. And because it's conservative, that means that we can find a potential vector field. So what we'll do is we'll say, first of all, that the first partial derivative with respect to x of this unknown potential function has to match this. So we'll start by saying it equal to that. And then we will evaluate that by taking the antiderivative of both sides with respect to x. Okay, so this over here is just the function we're after. And then over here, right, taking the derivative with respect to x, this would be x squared. And then this -3y is a constant, so it's a constant times x, right? And then plus some integration constant, but that constant could be a function of y, so we're going to call it gy. All right? And then the next step we'll do is we'll take the derivative of both sides of these things with respect to y. Right? So the result is that this is just fy now. And then the derivative of this with respect to y is 0. The derivative of this is, that derivative is 1 times the constant -3x, right? Plus the derivative of this unknown function we can just call g prime of y. All right. But then here's what we're going to do. We're going to say, all right, this fy has to equal this. So I'm going to force that to equal this. And then I'm going to take the antiderivative in order to get back to the original function, but this time with respect to y. So if you do the antiderivative with respect to y, we get back to the original function again. All right. So what is this antiderivative? Well, actually, no, we're actually finding out what y is. Let me just do the antiderivative operation here. I'm sorry, I skipped a step here. Let me go back to here. When we get to this step, and we've taken the derivative, we have fy here, and so we took the derivative and we got -3x plus g prime, and this was right to say, okay, that must equal this. So there's a step before I do the antiderivative. For y minus 8, okay? So since these things have to be equal, I could solve this for what g prime of y must be. Okay, so if I solve this equation, there's a -3x on both sides that will subtract out, and therefore we would say that g prime of y must be 4y minus 8. Because that's true, now I can take the antiderivative. So I have to get the gy by itself before I do this. I want to take the antiderivative of this respect to y to get what g is, this gy. Well, the antiderivative here is going to be 2y squared minus 8y plus some integration constant. So finally, I can substitute this back into this version of the function. I'll substitute it in here and rewrite the potential fx with the potential function of a function of both x and y is x squared minus 3yx plus the gy, which is 2y squared minus g8, or 8y plus k. Okay? So that is the potential function. And that's where this problem asked us, is asking us to stop. It's not giving us a field to actually integrate, or an integral to integrate. So that's the procedure for finding the potential function if we have a conservative field. All right, let's look at another example. Same thing, we're going to determine if it's conservative. So this is P, this is Q. We take the P, which is the X component, but with respect to Y, and the Q with respect to X, and see if those are equal. So P with respect to Y here would be, this is a constant. The derivative of cosine is negative sine of Y. Okay. And over here, the e to the x is a constant. We're questioning, are these equal? The derivative with respect to x. Okay, so that would be the copy, right, which is e to the x. And then the sine y comes along as a constant. So unfortunately, negative e to the x sine y is not equal to e to the x sine y. Close, but not quite. That means this is not a conservative field. And there will not be a potential function. No potential function for this. Okay, they have to be exactly equal, including their sign. All right, let's do another example. Evaluate this line integral for this field if c is the arc of the parabola y equals 2x squared from here to here. Now, if this turns out not to be a conservative vector field, we're going to have to parameterize this curve. Okay, and then go through the whole thing of doing the integral with the parameter. But before we go to the trouble of parameterizing the curve, let's first see, is this a conservative vector field? Is F conservative? Okay, so let's check. Here's P, here's Q. So let's see, partial P with respect to Y, is it equal to partial Q with respect to X? Partial P with respect to Y is 0. Partial Q with respect to X is 0. Those are equal, so yes, this is conservative. And because it's conservative, that means we should be able to find a potential function. So let's do that. Well, we know that therefore f of x, where f is the potential function f, the partial derivative of x has to be equal to x squared. And that means we can take the integral with respect to x to find our first version of that. Our first version of the potential function is going to be the antiderivative of this, which is 1/3 x cubed plus some constant, but the constant could be a function of y. Okay, so the next step is we'll take the derivative of both sides of this, but with respect to other variable y, which will give me fy. And so this is, there's no y here, so this is 0, plus the derivative of that is g prime. Okay, and then the operative point here is that this fy must equal y squared. So that means that g of prime of y is just equal to y squared. And so now I could take the antiderivative with respect to y of both sides and get back to what g is. So the antiderivative here is 1/3 y cubed plus an integration constant. So finally I can write my potential function. My potential function was this, right? It's f of xy is 1/3 x cubed, but now I have to fill in what g of y is. It's 1/3 y cubed plus k. Okay, so now that I have a potential function, I can use that to evaluate this integral, right? So when we evaluate the integral of that function, dr, should have been arrows there, okay? Well, because this is conservative, it's just going to equal f for the endpoint minus f for the start point, right? And that means we have to take the potential function, which is, we got 1/3 something cubed plus 1/3 something cubed, right? And then I have another copy of it, 1 minus another copy of it. And I have to evaluate this one, this first one. So the endpoint is this one. So that means we're going to put its x and y value in here. So the x value would go here, and the y value would go here. And then since this one is the start point, we're going to put that one here, right? End minus start. So this would be the x goes here, and the y goes here. And so if you plug all that in a calculator, you end up getting that this is equal to 171, okay? And although there's more work to find the potential function, potentially that's less work than parameterizing this parabola, right? So it's particularly nice if you have a really complicated path, because it might be very difficult to parameterize, or you might have to parameterize along different segments with different parts and have multiple integrals outlatted. But if you can show it's conservative, then you just have to find the single potential function for the field and then plug in the endpoints. All right. Okay, so that's a really good example from start to finish to show everything. That'll conclude the video here.